Thanks everyone for coming today. My name's Elize Papineau. I am a senior data engineer here at DBT Labs. And today I'm going to be telling you all the technical details about how we optimize the performance of our DBT project running on the Snowflake data platform. OK. Let's get through the agenda first of what we're going to be talking about today. So first, I'm going to do a little bit of a deep dive on the background of the problem we were trying to address. Next, we're going to talk about the specific platform infrastructure that we leverage to analyze the performance of our DBT project. After that, we're going to talk about the performance improvements that we saw without refactoring a single model. The outcomes of this were of the initial rollout, so we saw some really fantastic wins. And finally, we're going to talk about how we deepened platform knowledge on our data team. The summary here is thinking more about building DBT models to run on Snowflake than just building DBT models. OK. At DBT Labs, the internal data team loves using DBT, and we try to center as much of our data stack around the tool as possible. We use it for transformation, and we also use it for some other fun stuff that I think really pushes the bounds of the tool. We're also early adopters of DBT. And while this is fantastic, it does have some drawbacks. This graph here shows you the growth of one of our largest tables over the last 6 years. I love the 2018 because there is actually like several thousand rows of data there. But on this graph, there's not even a single pixel for 2018. And you can see that by 2023, the contents of this table grew to over 20 billion rows. Some other fun facts about our internal analytics project. The first commit to this project was in 2016. Today, we have over 1,200 models, more than 2,000 tests. And our largest models, the ones that we're going to talk about, the performance we optimized today, represent 18 terabytes of data. These older models were built, again, as this graph demonstrates, when rows were in the thousands. Today, they're in the billions. We're going to review how we optimized our DBT project for running these models on Snowflake and what we did to enhance performance of these queries that were not designed to run at this scale. OK. Before we go any further, I want to talk a little bit about some specific Snowflake architecture details that are going to be really important to keep in mind while we go through this. This graph charts the cost and execution time of a given query across Snowflake warehouse sizes. It may seem counterintuitive, but for a while, as we increase warehouse size, cost remains flat while execution time drops. That's what the red box there indicates. The takeaway here is that we can up our warehouse and offset the expense of the larger warehouse by seeing more performant queries, more efficient queries. We're going to talk about how we applied this principle to our DBT project at scale. We've spent the last year auditing and applying Snowflake best practices to our project. About 6 months ago, we started to see some performance degradation that we had to do something about. OK, and here's the graph that demonstrates that. What this shows is the 4-hour threshold of how frequently we run our main DBT cloud job. This job, like I said, runs every 4 hours. So when it starts to approach an average runtime of 4 hours, we were concerned. This became a cost concern. This became an efficiency concern. This became a maintenance concern. We wanted to fix it. I'm going to talk about what we did in May and then in June to bring this average runtime down, again, without refactoring a single model. OK. First, we're going to talk about the infrastructure that already exists today if you run DBT on Snowflake that enables you to do this type of optimization. Again, your first instinct here may be, I need to refactor some models. But I would invite you to take a step back and do some pre-work so that you can start to understand where refactoring is really going to have the most value. OK. This slide shows a top-level view of the tools that we use that exist today between DBT and Snowflake to allow us to look at our model's performance. First, Snowflake query tags. These create a one-to-one relationship between DBT model invocation and a Snowflake query ID. These are essential for doing performance analysis. Second, Snowflake makes metadata views available to you that tell you about the performance of specific queries and about the size and other attributes of the objects that exist in your warehouse. This enables us to identify trends around various Snowflake query statistics, depending on what you're trying to optimize for or what you're interested in. Finally, the modeling we did in DBT on top of these Snowflake views enabled us to codify some performance thresholds that were really helpful for our team to actually set the lines of when we decide to increase compute resources versus when we don't. Lastly, we're going to touch on the DBT configurations that allow you to tweak what compute resources are getting used, even if it's a different compute resource defined in your DBT profile that's connecting you to Snowflake. OK. Snowflake query tags. Again, if you're going to take one thing from this talk today, I hope it's Snowflake query tags. I hope you go and set something up here to enable yourself to at least do this work in the future when it's necessary. So what you see on the left here is an example of a query tag. I've simplified some of the values here in this query tag. But what you can see is here we're tracking the DBT environment name, some other DBT level variables, and then we're also tracking some DBT cloud level variables. Each Snowflake query object has a query tag associated with it. And what's helpful is when we execute a DBT model against Snowflake, DBT uses a macro called setQueryTag to set the query tag on Snowflake. The default has a little information, not the most helpful. And luckily, DBT enables us to customize its behavior. We can override the behavior of the setQueryTag macro to include all and any information you would like to track. In our case, this is about the example. If you follow this QR code, I've put an example of that custom macro that we have in our project up on GitHub for folks to use. Again, if you're going to do anything today, please go set this up in your project. You're going to be enabled to do this analysis in the future if and when you need to. And if you don't need it, you at least have the data there. OK. Once we've started to track information about which DBT models are associated with which specific Snowflake query invocations, we can actually start to do some performance analysis on top of them. Here, we're going to use the Snowflake metadata views to inform us. Snowflake provides a bunch of information to us about our Snowflake instance at different grains. Some are in the information schema at the database grain. Others are in the Snowflake database in their account-wide statistics. This at the bottom is the DAG of the DBT models we built to analyze the contents of these Snowflake views. It's very meta. It's DBT models about the performance of DBT models. OK. The query tags are specifically available in that query history view that you're going to find in the Snowflake database. It's in the account usage schema. We unpack those query tags because they are passed as JSON. We unpack them in the staging model for the query history view. And then we aggregate the statistics to provide recommendations in a downstream model. Here, for shorthand, I'm just calling it warehouse recommendations. In that recommendations model, we codify the recommendations of what compute resources we define as acceptable and what we define as unacceptable and in need of optimization. OK, how do we know if it's in need of optimization? This is a rough idea of the two thresholds that we use to define compute recommendations in our project. Our most weighted field is spillage. If you have local spillage or remote spillage on a Snowflake query, it is a performance killer. It is a performance killer. I'll say it like 3 times. If you're seeing that, it's a pretty sure sign you need to optimize the resource that your query, your DBT model is running on. Especially if you're seeing it happen repeatedly over a DBT job that runs several times a day. It's a pretty sure sign that you need to be using a larger compute resource. OK, so we use query spillage to categorize efficiency. We've called it efficiency, and we rank it as good, appropriate, poor, or very poor. In our project, we say if your efficiency is poor or very poor, it's time to upsize the warehouse. We also look at object size in gigabytes and in row count. And we recommend a warehouse size based on those. When we apply these rules, the DBT model that I showed you in that previous slide prescribes the appropriate compute for all DBT models in the project. So we get project-wide analysis of our performance on Snowflake. So what do we do with that? We then take it and turn it back into a DBT configuration. If you're using the DBT Snowflake adapter, you have a parameter available to you in the config block called Snowflake Warehouse, and this is an example of updating just that parameter. The results from that recommendation get pasted as the value or argument into this configuration, and it happens at the model level. What that means is if I have model A, which I want to run on my default warehouse, we don't update it. If I have model B that I want to run on a larger warehouse, I would update it. And for that model B example, when we invoke that model from DBT, Snowflake issues a use warehouse command in that session so that just that model is going to execute on that elevated warehouse. Okay, before moving on to results, let's talk about how we rolled this out to our data team. We surfaced warehouse recommendations through a Hex application. We ran a proof of concept with 5 models and monitored changes in query performance for those models in May of this year. After a week, 4 of those 5 models had clear gains, and 1 didn't. We reverted the change for the 1, and we decided that was a really good candidate for refactoring. We then implemented our recommendations for the remaining models that had them. This happened in June of this year. We've also built it into a rotation process. So every Monday, we have someone who is assigned to a support rotation that goes in and checks this Hex application for a new recommendation, and if there is one, they implement it. You can think of that recommendation almost as an A/B test, a type of experiment. So how do we define if that experiment is successful? This is a part of the Hex application that we use to understand if we actually want to keep the model running on elevated warehouses. In this example, the control, which is teal, I believe, is running on a medium warehouse, and the variant is the same model running on a large warehouse. The graphs are looking at average cost per run. They're looking at average execution time and average spillage, both local and remote. As you can see, we saw 100% reduction of remote spillage in this experiment. That's a success. We also saw a decrease in execution time of about 83%. That's a success. But what's even more helpful here is it's not up to the interpreter whether or not this was a success. If you look in that top corner, you'll see the green square that says successful experiment. And this is one thing that we really wanted to make sure we did when we rolled this out, is making these parameters very clear to our team, very straightforward to use. Sometimes the experimentation doesn't work. Here it did. Again, these are the same stats you might be used to viewing in your Snowflake query profile, but here we've aggregated them across DBT invocations. One of the takeaways here is there's many knobs to turn when it comes to optimizing your DBT project performance. We just found this to be the one with the clearest signal and the most obvious results. Okay, let's move on to the actual findings here. The outcome of this work was big wins with no refactoring. We optimized 26 models in our project. The takeaway from that number is that it's a small fraction of our project that was responsible for pretty serious performance degradation. The models that we tried to optimize but were unsuccessful experiments, we understood to be good candidates for putting in refactoring efforts. Our DBT Cloud job time dropped on average by 45% to just over 2 hours. We were very happy to see this. It gives us a lot of space to grow and to add to our project, which we're doing every day. Finally, because we're running more efficient queries, even though the job is running faster, we actually saw savings. We saw approximately $22,000 annual savings here. I'm going to dive into a couple specific examples here. Okay, first, compute. This is actually that same model I showed you the graph for the row count increasing on earlier. Today, that model represents 9 terabytes of data. On a large warehouse, the average query time was $31. 31 minutes. On an extra large warehouse, the average query time was 4.3 minutes. And this translates to a 78% decrease in cost despite using a larger warehouse, despite it running faster. I mean, it's like a win-win-win. Of those 26 models we optimized, the majority had those very poor efficiency rankings, basically remote spillage, local spillage, that we were able to alleviate by simply increasing the warehouse size. We also improved the query efficiency of these DBT models in general, and we're pretty stoked with these results. This was kind of the expected result, but we had some unexpected results as well that made us even more excited about this process that we were starting to implement. We also identified models that needed to have their materialization strategy changed. It's a generally held DBT best practice that when you first implement a model, start out with a view or table materialization, and then only increase to an incremental materialization when you have a reason to. Well, when someone goes in and builds a model on a brand new table, maybe one tracking DBT Cloud API requests, it might be a small model. There might be very little data, and a table materialization is probably the right choice. That being said, after collecting information for several months, that table got pretty big. And the appropriate materialization strategy was now an incremental. This is a really difficult thing to hold in your head, especially when your project is on the scale of ours, and especially if your project is much larger than ours. How would you know to go check this one model? And this was one thing we found that was really fantastic about our performance analysis, is that we were able to understand which DBT models we should go and examine for incremental capabilities. Not every model can become an incremental model, but we were able to create several incremental models that were previously tables. Okay. Cumulatively, we decreased our average DBT Cloud runtime by 45%, thanks to increasing the compute resources we were using, as well as changing the materialization strategy to a more appropriate one for certain models. You can see the results on this graph. In April, we were very close to that 4-hour threshold that we defined as unacceptable. In May, we rolled this out to our 5 largest models and saw pretty exciting results. And in June, we rolled this out to 26 models total and fully realized the results of this initial project. However, there's been more than compute performance improvements as a result of this work. There's been a pretty big human impact too, and this is one I'm extra excited about because I love seeing our team take ownership and moving deeper in our stack with a better understanding of how to build DBT models to execute on Snowflake. First, we have a prescriptive recommendation for optimization. This is really important when you have a team so that no one individual is ever questioning, should I change this, should I not, and left in limbo, or applying different levels of standardization. Our prescriptive model recommendations give an explicit yes or no if we should increase the warehouse size that the model is executing on. We also have an explicit yes or no that we check in after a week of running on that increased warehouse to ensure that we actually saw the results that we want. And it's never left up to the interpreter. Team contributors don't have to repeat this analysis. We just make it available to them. Additionally, we're moving deeper in the stack. The data team is not just thinking about DBT models. They're thinking about Snowflake query profiles. They're turning those Snowflake query profiles into tangible DBT modeling choices. And that's been something I'm so excited to see as someone who loves to look at a Snowflake query profile. Finally, we have really limited resources. And I'm really happy to know that we can start to understand exactly which models are the best candidates for refactoring. Okay, let's take a little bit more of a look at what this looks like. Okay, optimization recommendations. We, in our Hex application, where folks are consuming this data, explicitly say, this is where you put this configuration. This is the model that maybe we should try running on a larger set of compute resources. This is the model, this is the compute that it's using now. This is the efficiency ranking, here in this example, very poor. And then we even give folks a pasteable configuration. There is no guessing work here. I just need you to copy it and paste it in the model, and let's look at it in a week. These clear definitions are really important so that the whole team knows which levers to pull when and when to dial changes back. Okay, second, thinking about moving deeper in the stack. What does that look like? We're starting to see folks like Erica Louie, like Brandon Thompson on our team talking about this optimization hex application in GitHub, in Slack. It's getting pretty exciting. We've got folks who have seen, okay, I changed this from a medium warehouse to a large warehouse. Well, what would happen now if I moved that where clause a little earlier in the query? What would happen if we actually tried manipulating specific other attributes of the query? And we're all thinking about specifically, why are we seeing the Snowflake performance we're seeing, and what could we do to try and change that? Okay. Finally, human resources lived well, are used well. We want a happy data team. I want to see these smiles every day. Just like you, our data team has extremely limited resources, and we want to do as much as we can. Sometimes increasing the warehouse size is all that's necessary to ensure that your dbt model is running effectively. Other times, refactoring is the appropriate choice. Again, there's a lot of knobs that we can be tuning here. Models with failed optimization experiments become our prime candidates for refactoring. We're putting our human time to the best use that we can by going through this exercise. Okay, really quickly, I want to recap here. The infrastructure already exists to improve the performance. Again, if you're going to do anything today after this talk, go implement query tags. So in the future, if you ever want to do this kind of work, you have that data available to yourself to do it. Secondly, you can find performance improvements without refactoring a model. Sometimes having an automated mechanism to inform you when you should tune certain things is actually more effective than going in and investing 10 hours thinking about how to change your analysis with the same results. Lastly, you can deepen platform knowledge by engaging the folks on your team and helping them understand the tangible effects of implementing some of Snowflake's best practices. And finally, I would not be up here presenting this if it wasn't for the help of a bunch of folks at dbt Labs. First and foremost, Brandon Thompson, who did the majority of the work on the hex application that made this data available to our whole team. Matt Winkler and Lauren Benezra, who I would not have a talk or this whole query tag thing without. I want to thank the GitLab folks for open sourcing their project. We learned a lot from them, and we took that and ran with it. And finally, I want to thank the dbt Labs data team for being so open to letting me be a little crazy about tuning some knobs. All right, and finally, I want to thank y'all. Thank you for coming today.